Good morning, my name is Likith Reddy. I will be teaching the subject Signals and Systems in this video series. These are textbooks prescribed by the university for this subject. A.V. Oppenheim, Signals and Systems, and B.P. Lapis, Signal Systems and Communication. I preferred using the first textbook for all the notations in this series. The first unit in the series is the Introduction to Signals and Systems. In this unit, we have the following topics. The first one will be how to define signals and how to define systems. And then we'll see how we classify the systems, what are the different types of classifications we have there. And the same for systems, how do we classify the systems, and some problems based on those classifications. And then we'll move on to the basic operations we can perform on any given signal, and convolution and correlation of signals. And finally, we'll move on to analogy between vectors and signals. The byproduct of this topic will be the last topic, that will be Fourier series. So first, let's move on to definition of signals and systems. Signal can be defined as a function of one or more independent variables which contains or carries some information about a physical phenomena. Here, we defined a signal as a function of one or more independent variables. So based on the number of independent variables, we can further classify the signal. That is, if we have just a one independent variable, we call it one-dimensional signal. If we have more than one, we call it a multi-dimensional signal. For a one-dimensional signal, we can consider the examples of audio or speech. You can listen. You can take my speech as my lecture as a one-dimensional signal. My audio keeps changing with respect to time. From the starting of the video till the end of the video, you can see different modulations in my audio. That is a one-dimensional signal. With respect to time, my audio amplitude is changing. That is one-dimensional signal. Then in case of multi-dimensional signal, we can consider if we consider we have two independent variables, we call it a two-dimensional signal. If we have three independent variables, we call it three-dimensional signal. Any more independent variables, we call it in common as multi-dimensional signal. Images are examples of multi-dimensional signal. This is one-dimensional signal examples, speech, ECG, and this is the two-dimensional signal, image. Every row and column here, this is the row and this is the column. Every unique, you can consider this as a matrix. So first row, first column, there is some value. First row, second column, there's a different value, and so on till the last row, last column. So this is a two-dimensional signal. For three-dimensional signal, you can consider the example of a TV signal. What do we have in a TV? We have the video or the image. So image is of two dimensions with additional audio. Audio is a single dimension. So combine both two dimension plus one dimension, we get three dimensions in TV signal. That is a multi-dimensional signal. And then we can represent any given signal in two different types. The first one will be the graphical representation, and the second one will be mathematical representation. In the graphical representation, we draw x-axis versus y-axis. In the x-axis, we will always have the independent variable, and in the y-axis, we'll have the dependent variable. The amplitude here is dependent on time. As time varies, the amplitude is varying. So the amplitude is on the y-axis and time is on the x-axis. And the mathematical representation will be in the form of an equation. How can we represent this variation of amplitude versus time in terms of an equation? Y of t is equal to sine t. So the same thing, graphical representation will always have independent variables on the x-axis and dependent variables on the y-axis. And mathematical representation, the value of the independent variable y of t is written against the value of the dependent variable. So far we have seen what is a signal and how can we represent them. Then moving on to systems. What is a system? It is an entity that manipulates one or more signals to accomplish a function, thereby yielding a new signal. So these one or more signals will be the input to the system, and this new signal will be the output of the system. This accomplishing a function, that is the actual purpose of the system. So the entity that manipulates one or more signals to accomplish a function, thereby yielding a new signal. So it can have one or more signals as an input, and it will give us a new signal as an output. Another definition will be a set of elements or functional blocks which are connected together and produces an output in response to the input signal. One example for this system will be a telephone. It's a series of functional blocks. We have the receiver from one end, receiver at the other end. Both are connected via some media, some channel. So that will be the functional blocks, a set of elements or functional blocks, both the receivers as well as the channel. They are connected together through each channel. It produces an output in response to the input signal. The other side can hear some voice only if I give some input signal. I say hello, he hears hello. I say hi, he hears hi. I say okay, I'll see you later. He'll hear the same thing. So it takes one signal as an input, it processes it and sends to the other end, and there it is considered as the output in response to the input signal. So pictorially, we'll represent a system in this way. A system has an input function or a driving function. Driving function is just another name for input function. The driving function x of t is given to the system. H is the system function, and it provides us with a response or output y of t. So we are giving an input function x of t to the system h, and it gives us an output y of t. So mathematically, how we'll represent it? Y of t, the output is nothing but h of x of t. Here h is nothing but the transformation function, how we are transforming the input into output. So y of t is transformation of x of t. Symbolically, we write it in this form. X of t gives y of t via h, or x of t produces y of t via system h. Filters and amplifiers are the simplest examples of system. I give 1 volt as an input, and I'm sending that I'm giving a 1 volt input to the amplifier. The system is the amplifier, and the output will be from, let us say, 10 volts. And similarly, filters also. Some other examples of the systems will be camera. It takes light as an input and the objects as an input. So multiple inputs are there for camera, and it processes this information and it produces a image, 2D image. This is a signal, right? This is also a signal. So 2 signals as input, 1 signal as output. So this is a system. Similarly, speech recognition. So it takes an audio signal as an input, it identifies who is the person speaking. That is the output. The process that happens within the system, within the computer, so it is called a system. So similarly, we can also consider traffic lights as traffic lights. So let us say we have traffic lights on the input side, red, green, and yellow, and here it gives us some output, right? So let us say the traffic light, we can see red light glowing. So what does our brain do? It processes this information. So there is red light showing, so it gives us a signal saying stop, you have to stop at the junction. So it gives us the signal and asks us to stop. So what is the signal here? Traffic light is the signal, and it is giving us an output signal. It's asking us to stop. So what is the system here? Our brain is the system. So that is also an example of system. Other examples: a circuit, a control system, communication system. We've already discussed this, right? So this is nothing but what we thought of as a telephone: the message signal and the estimate, or the received signal. Input signal, received signal. So that is the end of introduction for signals and systems. In the next video, we will see how can we classify the signals and systems. Thank you.